Hello everyone, I'm Alec, I'm the organiser of the Edinburgh Golang Meetup. Thanks for coming tonight. First I'd like to say a big thanks to Monzo for co-hosting this with us. Monzo! Big thanks to Izettel as well for the help us with the room. And big thanks to Codebase, the hosts with the most. So we've got three great talks for you tonight. We've got Quinlan, we've got Alistair, we've got Charlie, and they're going to blow your socks off. So take it away, Quinlan.
All right. This is Go. It's a game. Don't know who knows it or not. The idea is to surround territory. So in this game here, this works actually. This is sort of all black's territory there. Well, that's the idea. And white's trying to get something. Black is winning if white doesn't do anything. So the idea is just to surround territory. And what's the other terminology you need to know? You need to know what a hane is. So what just happened there when those stones went out and black played at the top, that's called a hane. And it just stops these white stones from continuing going forward. That's all the Go you need to know. And then I can start the presentation. Somewhere we'll start there. Yes. So I am going to be talking about, I'm going to give you three proverbs that are Go proverbs. I'm not just showing half stuff. And then we're going to talk about the permissions module. Our permissions module at Make It Social was put together not by me, but one of our devs. Very good work. And it's just my character to talk about what other people do more than what I do. And DDK is a double-digit Q. It means I'm very, very, very bad player. So if there's any better players here, anyway, I'm saying proverbs, so not mine, so it's not me. Member invited notification request. So Make It Social has a product that when you want to go somewhere, you want to go with your friends, you go to Make It Social and you see, does Make It Social do it? And if it does, you can create a group and invite people. And then all of you guys can go together and everybody can pay for themselves so that you don't end up having to pay for everyone. And the member invited is done pretty much like this. There's an endpoint, there's a user ID, and there's a body. And the body is much longer, and so on and so forth. And we have a problem that we don't have a permissions module. So we started building one this year. We control access to this endpoint by the gateway, by firewall, and so on. But we do want to open it up so that anyone can access it and use it. So we need to create a permissions module. We started off with, this is the basic idea. There's a user, there's a role, there's a permission, and then there's an endpoint. So user is represented with the user ID, role, blah, blah, blah. And the problem is how we represent permission, because it can be an enormous array of things. And we didn't know, so we started off very, very practically. Being in Scotland, a permission is something that says I, or it says no. And the no is very, very, very important. And we didn't know what else. So this is all we knew. And this is what we ended up. Request user ID endpoint. You got to compare something in the request with something in the database, and the permission will say I or no. And where's this thing? Really? And this is what it looked like in the first iteration. We had our JSON representation over there of what the data is going to come in as. We had an interface for the permission. And this is just one I'm using for an example, group leader permission. So only the group leader can send an invitation to someone else. And the role ends up looking like that. And we like this, but there's a number of problems. Number one, how does this thing get the request data? Number two, what do you do when you've got more than one permission or more than one thing you want to check? Number three, how do you handle multiple endpoints that are going to be doing the same thing? So if you want to use group leader somewhere else, how do you do those? And I think there's one more problem that I didn't mention. I'll remember if there is. So first proverb, the greedy do not get success. And if anyone reads Mandarin, they can say if that says the same thing or not. Today, I'm the idiot that just copy-pasted. So if it says something else, I'm sorry. But I think it looks cool. I think it looks wiser because there's Mandarin underneath. And this is basically the Go version of you cannot have it all. So here's an example. First one, very, very clear, or let's say terse, name, email. Second one, not so clear, but saves on space. So you can have less space or you can have that. Third one, very, very usable. First one, if you need to figure out what the first name is, you can't. Whereas here, you can do it much easier. These are three different solutions for a particular problem, but each solution has its advantage that excludes the advantage of the others. So you cannot have it all. Much like the joke with the husband needs to be a cook and a therapist and a bodybuilder and this and all of that, and the wife just needs to be pretty, and the idea is the wife must also not look at your phone. This is the second thing, and the idea is that you have this long list of things that a man is supposed to be, and you can't have all those things. The greedy don't get success. The same happens in code. So when you have a problem that you need to solve, you need to figure out what am I not going to get, and figure out what you want. So how do we do one of the problems? How do we get multiple permissions to different endpoints? Because we don't want to write the same code all the time. So we abstract out the permission. So it's no longer is group leader permission. It's now is group leader comparer. And the permission holds the endpoint as well. So for every endpoint, we have multiple comparers. And what we sacrificed here is a lot of clarity because it's already become a lot more complex. It's no longer as simple as it was. But we have a way of solving the problem on how we reuse this bit of code for multiple different endpoints, and how we group many of these together for one endpoint. So if we want to say, is the member from London, we can add a comparer for that. Honey at the head of two stones. So exactly what we saw in there. When the stones were trying to make a line, we just placed a black stone in front. The idea behind this is that when you're going in a direction you don't want to go, you immediately stop. You don't carry on and then see where it goes. If you know, I don't want to do that, you're just going to cut that off. And this is the code example. So there is often this code that I really don't like. But it's not to say it's good or bad, it's just I don't like it. When I eat trifle, I like to mix it up because I think that's nice. My wife thinks that's disgusting. And I think this code, yes. So I didn't want to do this, and we stopped immediately. We're not going to do that. What can we do instead? And this is what we did instead. So we created a very big structure where we've listed all of these comparers. And leaning on the language facility, the JSON package, because I've got isGroupLeader over there, that thing will know to create an array of those when it sees that bit of data. And that allowed one not to, if it's that, then this, if it's that, then this. On the other hand, it adds the need for more unit tests, because anytime you have a comparer, you need to add it to that permission. So that permission ends up being, 50 or 60 lines long. But for me, that's better than if this, there, or switch, or a function map. The last proverb, so it was, what was it? Greedy don't get success, and honey at the head of two stones. And the last proverb is play the movie you want to play. And I couldn't find the Mandarin for this because someone said in 1970, so they haven't figured it out yet. The implication of this, I don't have an example for this, but the idea is there are things that the reason why we do everything right is so that we can do what we want to do. So if there's a particular thing coding-wise that you want to do, knowing that you've done everything else right, do that. Don't fuss about too much. When there's something that you want to do, do that. And this is what it ended up being for us. So one of the things that Ovidio wanted to do was to put an empty interface. And I hate empty interfaces. With all my heart, I hate them. But it was, he said, let's put this in. And he really wanted to do that. And, play the move you want to play. So we did that. And he said, why, and blah, blah, blah. And I didn't really listen. A week later, I started thinking about it, and it made sense. Because having done the things we did thus far, we know that this endpoint, that one there, is always going to get the same data. That endpoint never gets different data. And because that endpoint always gets the same data, over here, we know what data it's going to be, because it's always the same data that goes to that endpoint. So even though we have this empty interface here, it's not empty, it's not unknown. The data type there is never unknown. The data type there is always going to be the same, because that endpoint is always the same, which followed from that we made that big permission structure that goes for one of those particular endpoints. So yeah, 3 proverbs that helped our coding style, that helped us resolve the problems of creating a permissions module. The whole module ended up being not more than 300 lines. It's about 200 or so lines. And then we've got many of these, but it's really neat. It's really, really neat. It works really well. And it's applicable across multiple domains. So greedy don't get success, honey at the head of 2 stones, and play the move you want to play. All right. That's it for me.
Anyone got any questions for Quinlan?
Oh. Yeah.
How easy was to fit this solution existing production code?
So this is why we came up with the solution, because it does not touch production code. All
Request gets posted to this external service. So it fits perfectly fine. That was one of the things that we really wanted. So that's why we got the data and the endpoint and the user ID. So we create middleware and post to this.
Are there any Go proverbs that you missed out?
Yes. Yes. Cool.
All right, thanks very much, Quinlan.
All right, I need to get rid of this.
The thing about Go is that it doesn't have exceptions like other programming languages. I mean, that's kind of a lie. It has a panic, but it's definitely an exception. And the error type is kind of the equivalent of the exception in another programming language. I picked the PHP throwable type because that's pretty similar to all of the other exceptions in most widely used programming languages. And also, I had the IDE set up so I could take a screenshot of it. So yeah, it is kind of, and going back to Go proverbs, there's one of the Go proverbs from Rob Pike, but the actual Go programming language proverbs, which says, the bigger the interface, the weaker the abstraction. And you can kind of see here that there's a lot of stuff in that interface that you don't really need out of an exception. I mean, when you actually throw an error or throw an exception in a programming language, 90% of the time, you just need to read the message and you can figure out what's gone wrong. Oh, this endpoint's not working. Okay, cool. Is there a code for this? No, not really. Do you need to know the file and the stack trace? Yeah, I'm sure you can find it. So in Go, it's a lot simpler. An error is anything that implements the error interface. And the error interface is incredibly simple. It just returns a string, and that string is the message. The thing about Go is that errors aren't special at all. They're values, just like any other type in the system. Sure, there's an interface that comes built into the language. You can use it. You can not use it. And because they're just values, they follow the same rules as any other values in Go. So in Go, you can return multiple values from a function. It's not a tuple like in other programming languages where you can pass it around and you can do things with it. It's just two values. And then you have, let's say you have something that can fail, you just return an error as another value with the value. And it leads to a really simple way of passing errors back. I quite like it. It's honest. It tells you that something can fail. And then you have to handle it. There's no, just leaving it there and thinking, oh, well, something will catch it or the program will crash. Because stuff fails. Day to day, stuff fails, as we kind of seen. And you should expect it. It's not an exceptional circumstance, and it's explicit in its signature. But the thing about that is it leads to this oft-repeated pattern of, let's try and do something, and if it fails, tell the other thing, the layer above, that I failed too, which is a bit repetitive and nasty. But yeah. So you've got to be careful with errors because they're simple. That doesn't mean handling them is simple. If you just return the error all the way up, you can end up in a really horrible situation where you get just the base error of the things that can fail. So yeah, I've failed to connect to some random server. What does that mean? What does that mean for my program? Why is it crashed? It doesn't tell you anything. So that's why you have to be really careful and make sure that you wrap the error and say, this has failed, the business logic thing, because I can't connect to this server. And that tells you a bit more. So it recommends in the standard library that you wrap your errors as they go up. But it still doesn't tell you a crazy amount about exactly what happened because you don't know what error it was. The string could have got mangled on the way up and all that kind of stuff. So this is a really good package we found by Dave Cheney, some guy, that you can wrap an error and it will do the whole nice printing thing. But you can cast this back into the base error type, the errors type, and you can get which error caused it. So you can find out a bit more about it. So I've got here a few patterns for dealing with errors in Go. This one is one that's a bit debated, but it's called a Sentinel error. And this is where you define an error as part of your public interface, and you have a global package variable of the error. And then when something fails, you check to see if it is this specific error. So let's try and select something from the database, and if there's no rows returned, there's a specific error for it. Use sparingly is what I'd say about using Sentinel Errors because they really quickly clutter up your API, and there's a lot of things you have to check for. And then on top of that, you can't really add any specific context. You can say there were no rows returned, but you can't say, yeah, there were no rows returned for this user, because then you can't compare it to that because it's no longer equal to that thing. Pardon me. So yeah, there's another kind of general pattern. So yeah, it's quite good. It's used in the standard library in the SQL package of saying that there's no rows returned. Then you have custom error types. These are a bit better. You shouldn't create a custom error type and use it like a Sentinel error. Go, if error is of this type, do something. Because it tells you nothing. You should assert your errors to be a specific type for some behavior. If there's no behavior behind it, then there's no point in converting it to that. One thing I've seen recently is in the Stripe Go SDK. They have about 15 different error types, all with the same methods on them. Now you're just doing the same thing. You're just checking if it's this error, then this thing has happened. It doesn't really tell you anything. There's no need for it to have any additional fields. You could just have a method that returns what specific type it is. It's not that great. So you should probably err towards using custom error types. You can see here I've got an example of let's try and save something to the database. And if it's a MySQL error, and their error code is some error code, I know that it's failed to insert. And let's say I don't care about it failing to insert because I just want to try and save something. I write really bad code. You can do that. So yeah, there's a few kind of do's and don'ts that I've already probably gone through. Sentinel errors, don't overuse them, but if they're out there, check for them when you need to. Error types, you should use them. And don't create a new type unless there's actually any different behaviors. And don't use them as Sentinel errors by just defining new types. Panicking. I kind of lied at first when I said that Go didn't have exceptions. It kind of does, but they're a bit different. Panicking. Panicking is kind of like an exception in that when you panic, it goes up the stack until there's a recover. And you shouldn't do that. Maybe. Because there's a few cases you want to panic. If something's gone catastrophically wrong in your program, you need to stop it because it's no longer going to keep going. Like, there's no point in keeping going. And another way is might want to panic is to catch programmer error, because Go doesn't have generics and a lot of things like that. So you can't. Its type system isn't as great at preventing a lot of things. So a good example of this is in the reflection package, where if you try and get the capacity of a type that's not a collection, it'll panic because you can check the type beforehand, and you should be able to catch that at writing the code time rather than at in production time. Also, probably don't use reflection as well. You can see here I've got an example of a panic. We've got something that can't fail because we're retrieving something in a map. And if you recover, if it panics, the deferred recover statement. So a defer and go is a thing that gets executed at return, like after the return, but not really kind of thing. And that will catch the panic. Yeah, so this is a little bit about errors in Go. Cheers. Okay. Any questions? Go for it.
Do you ever ignore errors?
If you want to, yeah. I mean, sometimes the error isn't important. If you know what it's doing, you can ignore it. You can catch an exception and do nothing, right?
Yeah. So, yeah, you can ignore errors. I mean, you should probably leave a comment telling someone that you have and why you have.
Yeah.
Yeah.
Great. Well, thanks very much, Alistair. Next up, we have Charlie. Go. So we'll be talking to us about why should you use a Golang for microservices.
That's right.
I'm breaking everything today. Right. I've got an extra screen.
Can't put it on mirrored.
Yay.
Can you get to coffee.com?
Yes. Why go for microservices? Or why Golang for microservices? First of all, hello. My name is Charlie. Technically makes me a banker, but I try not to think about that. What I am is an engineer, and I was asked to do this talk, or I was asked to do a talk, and I thought, great, I'll talk about the platform, I'll talk about Kubernetes, and AWS, and everything else. And then somebody at Monzo said, we have too many talks about the platform. Can we talk about something else, please? And I decided to not talk.
Sorry, I just dropped it.
Oh, I dropped it. Okay. Is that better? So, I decided to, this being a Golang meetup, what is it about Golang that most interests me as a platform engineer? And so, I thought, do the languages we use to build systems matter? Does it matter if we use Golang, or does it matter if we use Java, or Python, or anything else? And first of all, because we're talking about microservices, let's try and define what that is. And it's kind of easier to define what a microservice is by what a microservice is not. So, monoliths. Monoliths are functionally distant aspects that are all woven together. So, it's a very common thing to start developing a product, and then you end up with all of your different components that do different things in the same process, running as on the same hardware, on the same computer. Usually you've got components that are tightly coupled together and they're part of the same program. And that has a bunch of advantages. It means that using any component is an in-process call. Like if I want to use the component that formats the name on a credit card, it's part of my process, I can just call it. If I want to share data between components, it's easy, especially big data. If I have a big data blob of something, I can just give the component a pointer to that data blob and it'll work. And I can test my program if I need to without having to run some sort of integration test on the whole system. So there are some advantages to monoliths, but there are some disadvantages. The code base becomes very complex. So when you have a very big application, you have lots and lots and lots of components all in the same program. If you end up with multiple teams, you get very easy conflicts arising when somebody wants to make changes to one part and another part, and you end up with merge conflict hell, and you have to spend time doing pull requests and everything else. And when you want to change a single thing, you have to redeploy your entire application. So, what's an alternative? Let's talk about microservices. Microservices, they are components as individual services. So I may have a component that just works out what the name of a customer should be on a credit card, and its own service. That's the only thing it does. Each component ideally does only one thing. And I use the word ideally like an ideal gas, rather than saying this is what you should do. So I'm talking about an ideal microservice architecture here. You need to have simple inter-service communication, so HTTP REST, and components are loosely coupled. So changing one component doesn't really affect another component if they have the same interface. And if that sounds familiar, going back to history, that sounds very like the UNIX philosophy. Write programs that do one thing and do them well. Write programs to work together, and write programs that handle textures, because that is a universal interface. So if you're using UNIX and you do an ls and a pipe to grep to a pipe to something else, that's actually a microservice model. It just happens to be one from the 60s. So there are a bunch of advantages. Suddenly, your components are independently deployable. You can deploy the service that changes the name on a customer's card without deploying a service that does something more fundamental or might be more complex to do. You can scale your components independently. If a part of your stack needs to deal with more load than another part of your stack, you don't have to scale every big box, you just scale that particular service. It's much easier to understand your individual components. It means that a team that knows the name change on a credit card, they know that very well, and they might not know the rest of the service, but they don't need to. And it's a natural fit for containerization. When you've got tiny individually deployable components, it's a lot easier to think about sticking them in a Docker image, for example, or running them on a container platform. And all of that put together means that it's a lot easier to take advantage of horizontally scalable systems. If you have a lot of computers, but maybe they're not very big, that's okay, because all of your services are small, and you can run lots of copies across all those different computers. However, all is not rosy. There are a whole bunch of disadvantages to microservices. Suddenly, you have much more network I/O in the whole. Before, the call to your name changer service was in your same process, and you just called it. Now that's actually a network call over the wire. Deeply nested call chains are slow. So if your service A calls service B, which calls service C, which calls service D, each of those is a network call, and each of those are slower than it would be in process. Transferring large payloads is super expensive. If you want to give a service a megabyte of information, you have to send it a megabyte of information. It has to unmarshal that, copy it, maybe send it on somewhere else. It's really hard to do. It becomes harder to understand the whole system. It's much more sophisticated DevOps. And there are more disadvantages. With a big system, suddenly you need things like service discovery. If I want to find the service that's responsible for changing the name on a customer's card, I need to have some way of looking it up, like whether that's DNS or something else. Global transactions are hard to implement. When an action can touch lots and lots of services, how do you wrap that in a transaction? It's really hard. You may need distributed locking. You may need to start a lock at some point in your system and then release it at some other time. And then you've got, as the last point points out, all of your problems suddenly become distributed computing problems. And they're not easy. Before I talk about why Golang is a good fit for this, I'm going to briefly talk about the Monzo platform, which lets me get my fix of talking about Kubernetes and everything else, but in the context of Golang. And your software has to run somewhere. So we could talk about Golang in the abstract, but it's a lot easier to talk about Golang running on something. And Monzo's platform has all of these components. And I'll talk about each one of these very briefly. Our container platform is Kubernetes. So Monzo service is roughly 600 individual containers running on 300 nodes inside AWS. And each one of those components might be made up of up to 3 or 6 or 9 units that all do the same job. So we have horizontal scalability for each service. And all of this runs in AWS, and we use a bunch of other stuff for other things. Our infrastructure is 2 physical data centers to connect to the MasterCard network. Effectively, MasterCard gave us or sold us 2 huge boxes, and they're the only things that are allowed to talk to MasterCard, and that's the only reason we have data centers. We'd love to get rid of them, but we can't. And 350 EC2 machines in AWS, which run the container platform in our database stack. And underneath that, we have Cassandra as our underlying state layer. Our container platform uses multi-master Kubernetes and our own extensions to etcd. etcd is a distributed locking system that we've spent some time making a lot more reliable under failure conditions. etcd underpins our entire service. When you're running Kubernetes, etcd is the component that if it dies, you are catastrophically broken. Make sure that you keep etcd up to date. We have different instance types for different workloads. What that means is in AWS we run different sizes of instances. Most of our instances are quite small, but we have a few for services that require lots of memory. I mentioned service discovery before. and we use a product called Linkerd to find all of our components inside Kubernetes and to do things like retrying network calls that go wrong. So when you make a call from service A to service B, if something happens to service B and the call that you made was a simple HTTP GET, that's always retryable. So Linkerd will handle retrying that for us. All that out of the way, right? We can talk about Golang. What Golang features do I actually care about as a platform engineer for building a system, a distributed microservices system? Goroutines. So part of the Go runtime, a goroutine is a function executing concurrently with other goroutines in the same address space. That's wordy, but what it means is multiple functions that might all do different things, and they're scheduled at the same time. They're extremely lightweight, and under the covers, they're multiplexed onto multiple OS threads. So if I fire off 100 goroutines, but I only have 10 real threads, the Go runtime will take care of scheduling those onto the 10 threads and run them all to completion. You can invoke any function as a goroutine. So if you have a function already, it's very easy to invoke it concurrently, including functional literals. So that means you can define functions in line. And don't worry, there's going to be code examples immediately after this. Function literals are closures. And what that means is if you have a variable and before you declare the Go function, it will inherit that copy of that variable. And whenever a Go routine is blocked, so if you're waiting on I/O or something else, the Go runtime will suspend that Go routine and start another one. So the Go runtime will always start other Go routines that are not blocked. So it takes care of the concurrency problem of making sure that things still run. You end up not doing that. So here we have a Go routine example, which was the simplest one I could think of, where we have a function called sleep then hello, and all sleep then hello does is sleeps, and then it says hello. And so in our main, almost fell off the stage, in our main function here, we print going hello, and then we say go, which invokes the Go routine. It tells it, just go and do that, and continue processing. We print sleeping 10, sleep for 10 seconds, then finished. On the left, we can say going hello, sleeping 10, so we get the print before this happened, and then the function eventually gets scheduled, and it waits for 5 seconds, prints hello, and then because we've waited for 10 seconds here, the last thing we do is we print finish. So that's a Go routine. I mentioned that we can have function literals inside a Go program. So here is more or less the same program. We have the main function that prints going hello, and we have a message saying hello friends, and then we have this thing called gofunc. So gofunc is an anonymous function that does this job. It says message becomes equal to message, and that's a closure. What it means is inside this scope, as far as this scope is concerned, message is that copy of this message. We sleep for 5 seconds again, and we print the message. So we scheduled this function by saying gofunc, and then we change message to bye friends, and we do the print. Now, what we get over here is going hello, bye friends, sleeping 10, bye friends, finished. But that doesn't actually feel like that's what we wanted. Because when we declared the function here, message becomes equal to message. Like, I think the assumption was, since I wrote this, I know what the assumption is. The assumption was that this would inherit hello friends and not be bye friends. So it's important to note here that when you schedule a Go routine with Go, the runtime is in charge of when that actually starts. It doesn't start until some point in the future when the Go runtime decides to start it. So what's happened here is, before this function has started, we've already updated message to be bye friends. And therefore, when we hit message becomes equal to message, the value of message is bye friends. That's not great. So when we invoke a function, you can pass it parameters. So a function is just a regular function. I said you can go any function. So here, we go a func, and we pass it a parameter called message. And then at the invocation time of the go func, this will inherit hello friends. And we see going hello, bye friends, sleeping, hello friends, finished. I said that Go routines are lightweight, and I can make 100,000 of them, and it won't even blink. So my function doesn't do very much. I mean, all it's going to do is print the number that I passed it to and then sleep for 10 seconds. But if I run time for this program, it takes 11 seconds and it doesn't stress the system. It doesn't run 100,000 invocations at once, it will just schedule them to be run by the number of underlying OS threads. And it means that when you're writing goroutines, you often don't have to worry in the same way that you would worry in some other concurrency language. I don't have to worry about it the same way I would if I was writing Python async or Java threads or anything else. I can fairly safely spawn 100,000 goroutines and be quite confident that everything will be okay. Channels. So, if we have lots of goroutines running, a classical problem is how do these concurrent functions communicate, either with the main thread or with each other? And Go provides something called channels, which are typed conduits which you can send and receive messages with an operator. And they're an easy and safe way to coordinate goroutines. So my goroutine can talk to the main thread or another goroutine by sending a message on this pipe. And going back to the UNIX paradigm again, channels are like pipes. So if I do ls pipe grep, the output of ls is getting pipe to grep in the same way that a Go channel is coordinating my goroutines. We've got an example. So here, our main function here is making a channel of integers. So this is a structure that can accept integers. And the (4) here says that it can accept up to 4 integers at a time. So it's a buffer channel. You can write to it 4 times before it will block. And then we've got 100 goroutines that all attempt to write to the messages channel at the same time. And we've kind of scheduled them at the same time. And here in our main loop, we are parsing, we're reading from this channel and then sleeping for a second. So we have one consumer and 100 goroutines trying to write into this channel. And we run this program. What happens is 4 of the goroutines get to write and then they exit. And then all the rest of the goroutines block. They block on messages, send I to messages, because there's no more capacity in the buffer channel until this routine sums them and then finally frees up the channel to have more messages put into it. Go has very good core synchronous primitives. If you've used other languages and you wanted a singleton, you wanted something to happen exactly once, that's very difficult to do in a concurrent system. There is a sync primitive called once, where you declare that you only ever want one copy of this function to ever be run. You have wait groups, which are a simple way to block until all of your goroutines contained within them are finished. And that's super common. And then lower level than that, we have mutexes. So when multiple concurrent goroutines want to access the same resource in Go, that's unsafe. So if you have a map and you have multiple goroutines wanting to read or write to that map, you can't just simply let them read or write from that map, you'll get a crash. And so we have the option of using mutexes, effectively locking a map, reading from it, unlocking a map. The idiomatic way to do that kind of stuff, though, is to use channels and have something else manage your map. And here we have an example of wait groups. So my previous examples all had time.sleep10 at the end, just to wait until everything had finished. But that's really inelegant. So here we spawn 100 goroutines, but this time we're declaring this structure called a sync.waitGroup, and whenever we spawn a goroutine, we're adding 1 to the wait group. And then inside the goroutine, we defer a function to say waitGroup.done. So when this function has finished after the time.sleep, this waitGroup.done will trigger, and it will effectively decrement the wait group by 1. And then after we've triggered off our goroutines, we just have to wait for the wait group to finish, and then we exit. And so we have here 100 goroutines, and this time we don't have to wait for 10 seconds to make sure that everything is finished. We just do the time, and it took 0.007 seconds. The computer didn't even notice. Contexts. So when you have a distributed system, particularly one with lots and lots of small components, and you might need to have chains of calls. So my service to do something, it needs to call another service. That service has to call another service, and so on. There should be some way to know that that call chain should not continue. Maybe it took too long, or maybe some other event happened that meant that the work that that entire system is doing should stop. And the way that Go does this is via contexts. So contexts are across API and cross-process signals. When we have multiple microservices all running as individual components in their own processes, whenever we make a request from one to the other, we should pass them a context. And whenever those services make a request to something else, they should forward on that context. And this means that the parent, the originating service, is free to do things like say, I want to abort if this entire chain takes more than a second. I'm not interested in the result. And we want to avoid any of the computation that would happen if the original process did abort after a second, but there was still work that every other part of the system was still doing. And we do this with contexts. Here, this is the simplest example I could think of for a context. We have a function called worker, and worker takes a context and it takes a message. And its only job is to check to see whether the context is done. And if the context is done, it's going to error. But if it's not done, it's going to print the message. So it's either going to print something or error. And in our main function, we declare that we want a context based on the background context. That's the parent context that your program starts with. And it says with a deadline of 2 seconds. So this context is saying that I only want this to ever take up to 2 seconds. And if it's more than 2 seconds, we should probably abort. And then we call worker with the context hello, which prints hello the first time. And we wait for 5 seconds, so the context has expired. And then we call again with the context. And this time, in the select block, the worker knows that actually it should abort because it's taken too long. But the context has finished. And so the worker prints out context deadline executed. What other things are important that Golang brings for me as a platform engineer? It brings opinionated formatting using Go format. That sounds like a small thing. It's not. If you've got 30 or 40 teams and they're all developing and they all have their own particular style, it's really difficult to read somebody else's code. Go FMT formats the code the same every time. It has a diagnostic tool called Go Vet, which detects race conditions and common mistakes. As a beginner Go programmer, that's super useful. It has cross-platform compilation support. So I could compile a binary on my MacBook that will run on a Linux host or a Windows host. And key to me is it compiles static binaries with ease. So a static binary is an executable that has all of the libraries that it uses compiled directly into the executable. It doesn't use shared libs or call out to the DLL loaders or anything else. Golang has a really sophisticated garbage collector. The garbage collector minimizes stop the world events. So Golang's garbage collector is a mark and sweep garbage collector. It scans everything concurrently with your code, and it attempts to find objects that things may not have a reference to anymore. And then after it's built up a sufficient number of objects that it should look at, it stops the world for under 10 milliseconds, finds all the objects, works out if there's anything that can expire, and then kills them. So we see much less garbage collection, many less garbage collection events that stop processes running in our system. And it has extensive diagnostic tools that you can perform on live production services. If you build them into your services, you can end up, you can ask your service to tell you everything that happened to it in the last time window and get call graphs and everything else. And I'm going to attempt a live demo. And let's build a small, fully concurrent HTTP service and see what that's like. Okay. So this looks a lot smaller on my screen, but this is the HTTP service that I want to build. And this is an HTTP service that is going to insult all of us as quickly as it can, or as concurrently as it can. And we have here I've collapsed some stuff, but principles, adjectives, and actions are just lists of bad words. And we have a function called choose that's going to pick an item from a list that you give it. Then we have this function called geninsult, and this is us pretending to go to the database or do something slow. So geninsult sleeps for a second, and then it formats the string that's going to be full of bad words. We have func insult handler. Now this is the thing that actually services our HTTP request, and it's going to call geninsult and then return us the string. And finally, our main program, all that it does is it initializes the random seed for no reason anymore. I think previously geninsult waited a random time. So we do something useless, and then we register the insult handler on the /insult endpoint. And we should be able to build this. Ideally, we should be able to build this as a Docker image, which is what I really want to show you. So if I do cat file, here we've got a Docker file that's going to build our server. And the way that we're going to build it is using Docker's intermediately build containers. What's going to happen when we do Docker build is it's going to compile our program using static compilation, and then after it's compiled it, we're going to start a new container, a new image. From scratch is the basic Docker image with nothing in it. And then we're going to copy our static binary into that image. So we should end up with an image that has nothing in it apart from the binary. It doesn't have a shell, it doesn't have anything else. So there's nothing to attack inside that image, and it's going to be very, very small. So here we're going to build it, and then we're going to download 50 megabytes of stuff. That's pretty big. Just to build, 105, ouch, to build our executable. It shouldn't take too long. I'm glad the Wi-Fi is here. Yes, so we compile our program, and then we see that this is the compilation, run GCO enable 0. So we're building our insult server. And then finally, after that's all finished, step 7 of 9 from scratch. So we're making a new image, the scratch image, and we're copying that static binary into that image. And then we should have built something called insult server. Latest, brilliant. Let's find out how big that is. For some reason my T button does not work. Hey, so we built an image. So insult server is a Docker image, and it is 6.1 megabytes. So this is a fully featured concurrent HTTP server where the image is only 6 megabytes. That's right. Awesome. That did nothing, but we should be able to get some sort of insult out of this, hopefully. My entire talk has been a drive up to me insulting you. So. Yay! There we go. So, and with that, I am done. And I'll take any questions. Actually, wait, no, I have another slide. I totally forgot I have another slide. Yeah, so let's recap. So my entire talk could have been wrapped up in this slide. Why Golang? Golang lets you write high-performance concurrent components in a straightforward way. I don't have to worry too much about Go routines that might consume a bunch of CPU versus ones that block, because the Go runtime will take care of that for me. It produces small static binaries which run with modest resource allocations. We probably could have run that HTTP server a few thousand times on my computer. It's a great fit for microservice architectures in general, and for containerized workloads in particular, because the Docker images are so tiny. It means that if you have 300 or 400 instances, all of them running Docker, by saving, 100 megabytes for that image versus a JVM-based image, we are saving 100 megabytes times 300 instances in cost for I/O storage and IOPS that we have to provision. And this is why, as a platform engineer, I love Golang. And that's me. Questions? Yes.
Is the Uniswap server on GitHub?
Yes, it is on GitHub. Yeah, I'm not sure the best way for me to send that around. I'll talk to Alex and I'll broadcast it around for this. I want to write a blog post on this anyway. So. Yeah. Anyone else? Yeah.
Sometimes when companies have a microservice in a platform, it started out with a monolith or some kind of monolith remains with microservices around that. Does Monzo have experience with that? Is that something that you have?
No, we got super lucky in that Monzo's only 3 years old, and the people who started Monzo were coming from a monolith and really didn't like it. And so Monzo started on Mesos, but it started as a microservices platform from the beginning, which makes things so much easier. In the past, at different places, we tried to break out monoliths into microservices, and it's always really hard to do. Usually because you've got that tight coupling and you're passing big data blobs around, and it's difficult to get out of that habit.
Could you tell us what the biggest thing is
in Monzo?
In Monzo, just to get an idea, because the small things, that doesn't make sense, but
Well,
what would be the bigger thing?
Well, I mentioned that we have different instances for different workloads, and so our biggest containers are probably running things like our metrics platform, running things like Prometheus or Grafana. So they're not part of our call stack per se. They're not part of the actual bank. They're part of the tooling that goes around the bank. And I guess our build service is an example of a bigger container. So when we did that Docker build the first time, it had to pull 150 megabytes and it had to compile a bunch of stuff. And that takes up quite a lot of resources. We build all of our components inside our container platform, but we have a service that triggers jobs that maybe consume up to 1.5 gig of RAM and quite a lot of CPU for maybe the time it takes to compile the program and then deploy. So those are the biggest things in our container platform.
You got an example of where concurrency in Go is giving you like a big advantage, or like over like traditional?
Not at Monzo, because Monzo's been Go from the get-go. I have personal examples of, I wrote a lot of concurrency in Python async. So Python async, you have a single reactor, you have a single thread that runs everything, and you create things called futures, and your futures should always be I/O bound. You try and avoid doing computation on a future because the only way that the whole system will work is if you're waiting on some resource. So if you're going to get web pages or something else, that's fine, because your future does nothing apart from just wait until data is available. But if suddenly you start doing things like parsing XML or doing something else inside that future, suddenly the only thing running on your entire system is parsing XML. It's not doing things like waiting for the events to come in from the web service. So in Python async, it's actually very easy to get yourself into a state where the code that you wrote accidentally blocks your entire system. And in Go, that's still possible if I spawned a bunch of goroutines that all did computationally intensive tasks. We would probably see that as soon as we ran out of OS threads, nothing would get scheduled for a while. But as long as you're not trying to like build the Fibonacci sequence in all of your Go threads at the same time, for example, you want to avoid that. But no, I don't have an example for Monzo.
Are there any tips or insights on how you manage your dev teams?
Badly? No, flippantly. Our dev teams, so I'm on the platform team, and our platform team has responsibility for the platform, underlying platform, but we manage the AWS infrastructure, we support the Kubernetes container workflow, and we build things like the build pipeline on the metric system. In other teams at Monzo, because the whole reason we wanted to go for microservices in the first place was to increase our agility. We wanted to stop teams having to step in each other's toes. Then teams are structured around about the code that they build. They build it, they run it effectively. So our payments team is a good example, which is the core of the bank. So whenever you make a payment on Monzo, you're talking to APIs and servers that were developed by the payments team. And I talked about the name change card a few times. That's an example of just one of our services. So that the code that works out what your name should be on your credit card or your card when you get one from Monzo is its own service. And the only thing it does is take your name and then work out what your name should be if your name is too long. So we try and aggressively, we try and stay pure so that we don't have services that do more than one thing. And that means that we don't step in each other's toes.
And any ways of stopping separate teams building those same services?
Yeah, so that I alluded to, it's harder to understand the entire system.
Yeah.
I guess that's a trade-off that I feel quite comfortable with. I don't mind if two teams build the same tiny service. Eventually, if someone recognizes that, we can consolidate it, but the worst that would happen is that we end up using a little bit more resource for that service, which is probably better than two teams not building anything.
How do you tend to document that then? Is there a big sort of map?
Well, we have all of our code is in a monorepo, so a single repository. So when developers check out the repository, they're actually getting all of Monzo services.
Yeah.
And then we have a naming convention that's fairly logical. So it's like service dot, then your team area. So it might be service dot platform dot something or service dot payments dot something. And I think that reduces the footprint of being able to conflict. But I guess there's probably domains where you end up writing the same logic for two different teams.
You got visualization of it, at all?
I don't. There's something that we don't do at the moment. I made a course visualization of the Monzo code base, but I didn't really tell me anything. It just looked pretty. So no. And the back?
Use any specific microservice libraries or just listen and serve?
Yes, we have our own Monzo made its own microservice library called Typhon that is open source, and all of our services use Typhon. Typhon abstracts away some of the primitives that I showed earlier, like it handles the context for you and stuff like that. But we do use Typhon and an internal thing called Bedrock, which has all of our common application logic. So when a service needs to log to our distributed logging service, it does it through Bedrock.
So you guys are using Cassandra, aka immediate consistency. When you have to make it so that one thing, sort of data is always immediately available once it's happened, do you just use ECP for that? I don't really know how well ECP, or if at all, if that's the way you use for it.
I'm very tempted to say this is a Golang talk and avoid that question. But so the question was when we're using Cassandra and we need an instant reply, do we use a consistency level of 1? I'm not aware of anything that we need to do that. The way that we have code structured is there is a critical path for every transaction. So if you want to pay somebody else, for example, you might the core responsibility that ensures that payment happens may only touch 5 services. But for everything else to happen, so your phone to be notified that things happened or like some stuff to be triggered later might be 50 or 60. So the way we organize that is we have the core path is synchronous. It calls service A to service B to service C, and then we spawn a message on a queue, a distributed queue that says for the longer term, less critical, expensive things, somebody can do that asynchronously. So it's not part of that. And I think that would avoid the requirement for us to have to write something to the database and then read it straight away, because we could afford to write something and then just wait for it to become available.
So you guys are just relying on speed instead of making sure that someone just doesn't manage to somehow quickly enough pay twice with the money that he...
Oh no, I see what you mean, right. No, there's a very, very complicated system. It's called our ledger, and that ensures that it's effectively a write-only transaction log that So if, when you're actually making a payment on a critical path, yeah, the consistency level has to be met, and it has to be registered in Cassandra before things can happen. So if we try to write to the ledger and the ledger for some reason couldn't respond, we would have to abort that transaction.
What build system do you use, and how do you manage dependencies?
We use our own build system. We're currently looking for options in that. It's one of the platform team's goals for Q3 is to get is to have a more repeatable build system. So at the moment we have a service, like service.platform.build, that watches the repository, and when builds need to happen, it spawns a job in the platform that builds an image and then saves it to our registry. And that works. I mean, it works fine. It's just that we would like to use something that has a nice UI and that more developers can see the status of their builds. Yeah, I think I'm done.
Well, thank you to all of our speakers. It was really interesting talks there. And thank you again to our sponsor, to Monzo for helping us there. And to Codebase for hosting us. So if there's any pizza, grab it. If there's any drinks, drink them. And thanks for coming.